This unit's going to cover quite a few concepts and sort of rehash some of the old ones that we've used before. And states of matter and mixtures are kind of a lot of different parts that really make up this nice whole. Here's a quick overview. We'll be looking at chapters 10 and 11, and it's going to be helpful to kind of have some knowledge of bonding and molecular polarity in addition to several. But one of the biggest things that's going to be helpful is that those two concepts. And generally speaking, we're also going to delve into something called intermolecular forces, look at states of matter and how phase changes can be explained by intermolecular forces, learn how to do calculations involving concentrations, learn about mixtures, a couple of different types of mixtures, colligative properties, and then colloids to finish it off. So this first bit is going to be a bit of review, actually, for something called the kinetic molecular theory. This is basically a fancy way of saying, how do the particles' behaviors explain what the states of matter do? So let's go ahead and break this down. First of all, states of matter, you should recognize that there are three main states of matter: solids, liquids, and gases. Nothing new. But then, of course, what exactly dictates why water, for example, is a solid, or when it's ice, or when it's water vapor? How exactly is that explained? It's not as simple as just saying, it's hotter or colder. Furthermore, you also might notice in this top right corner here, if you're looking at the states of matter, you have the solids, the liquids, the gases like usual, but then there's also two other ones. You have plasmas, which again is kind of this fourth state of matter, which is something a little bit beyond what we need to care about here at this point. But it basically describes like a really hot, flowing ionic set of particles, or ions in general. And then on the left side, you have something here, Be. It's abbreviated Be. It's actually the Bose-Einstein condensate. Those are different type of states of matter, which really refers to sort of the very tiny, super basic elementary particles and their behaviors, which again we will not get into because that's well beyond the scope of what we know. But just know that there's more than just those three normal solid, liquids, and gases, but that is the focus of what this section is on. It all comes down to the relationship between the kinetic energy of the particles and the intermolecular forces that exist between them. So first of all, kinetic energy, again, this is the energy of motion. Effectively, temperature is how we measure kinetic energy, where high kinetic energy means high temperatures and vice versa. Low temperatures is low kinetic energy, nothing surprising there. And then intermolecular forces, which are these attractions between the different particles of a sample. So the intermolecular forces is kind of like this sort of generic term, stickiness, I suppose, of how the particles are attracted to each other. High intermolecular forces mean that there's a lot of attraction between particles. Low intermolecular forces means that there's relatively low attractions between the particles. And again, you can sort of replace the word attractions with like something like stickiness. How sticky are the particles in relation to each other? So again, kind of the basic fundamentals here. It looks at the states of matter. You have the solid, liquid, and gas. This is from the left, middle, and the right there. So what are the relative kinetic energies and IMS for these? So in comparison on this one right here, right? In this case, the kinetic energy is going to be much, much less than the IMFs that are present. Here, the kinetic energy as a liquid, they're comparable, so approximately the same as the IMFs there. And then on the far right, this is where the kinetic energy is much, much greater than the IMFs that are present. So the intermolecular forces that are there keeping them held in place. And one thing to kind of keep in mind here is that the IMFs are all the same throughout this whole process. Because it's not like, so IMF is actually going to be directly or specific to the individual particles' identities. And these are all water, right? Water, water, water. These are all water molecules. And therefore, the amount of intermolecular forces that are present, they're actually all the same. It's just that what differs here is the amount of kinetic energy, the amount of temperature particles that allow your particles to then move around. So again, going back to this kinetic molecular theory, the theory that explains the behaviors of gases, liquids, and solids, really should be solids there, can be explained by the behaviors of its particles. So that all accounts for it. We've already seen this before, kinetic molecular theory of gases. The behaviors of gases can be explained with 5 tenets. The kinetic molecular theory, again abbreviated KMT. For example, gases consist of a large number of particles that are very far apart, right? The individual volumes of each individual particle is considered negligible. Also, the IMS between gas particles are negligible. Gas particles are in continuous rate of motion, and so on and so forth. So you've recognized these before, and that's how we can explain these various gas properties. For example, the fact that the gas properties can expand and compress, right? Expansion comes from the fact that you have a large number of particles that move in constant random motion. And so if they're focused in one small part, or they're at least entering into a small part or injected anyway to a small corner of a larger volume, right, these particles are eventually going to spread out and move around the entire sample or entire container, right? It's a constant rate of motion. They can also compress, like you see here. Right, this is compression over here because there's a lot of empty space between them, right? You can force these pistons to make these particles be closer to each other. So again, this is all being tied back to those 5 tenets that we just stated before, right? So the reason why these behaviors and these properties exist is because of the kinetic molecular theory on the previous slide, and some combination of those that explains these. When it comes to liquids, again, this one's a little bit more focused now. The kinetic molecular theory on liquids shows that the particles are in constant random motion. So again, that's not surprising there. We've seen that before. The particles are separated by very little empty space. So now we actually have them be a lot closer to each other. And there's not a lot of free empty space that these particles are, again, free to move around in. And number 3, the IMFs of the particles have a moderate role in behavior, balanced with the kinetic energy of particles. So as a comparison, remember the intermolecular forces of gases are practically negligible. I mean, they're present, but again, for the whole big picture, it doesn't really play a big role. Liquids, however, they play a moderate role. They're still around. They do hold these particles reasonably close and don't allow them to freely move about. Last one here, liquids and gases are categorized as fluids due to the freedom of movement of those particles, because again, they're generally able to flow past one another, and therefore fluids is an appropriate term to refer to them. Liquid properties here, relatively high density. Remember, high density because the particles don't have a lot of empty space. So there's a lot of mass, right? Lots of little particles that are held close together. Relative incompressibility, right? So these you can't really force them into smaller spaces because there's not really any empty space that they can be forced into. And then, of course, they're able to diffuse. Of course, diffusion meaning the ability for them to intermix and intermingle, because they're in constant random motion, right? So you have right here, you have pure water. You inject a little bit of dye in there. That dye is, again, all very concentrated at first, but over time, it's allowed to spread out and disperse because, or diffuse anyway, because they are also in constant random motion. A couple other properties about liquid: surface tension. This is like a force, or it's a kind of a tension that is at the surface there. It's a force that tends to pull adjacent parts of a liquid surface together, thereby minimizing surface area. Right, so somehow, some way, these particles are again kind of allow for this extra little bit of tension at the top. That allows, again, there to be some extra sort of a force that you can put, like, things on, right on. For example, here, this little water strider. These water striders can kind of ride along the surface of water because there's this inherent tension that the water allows you to have at the surface. The more intermolecular forces that are present, the more intermolecular forces that are possible, the stronger the surface tension. And this is something we'll talk about some more in greater detail. On the right side of here, this is actually a particle view that's a bit more, I think, hopefully enlightening. So if you notice, right, these particles right here in the middle towards the bulk of the sample versus these particles here that are the surface. The ones that are in the bulk, right, notice these little arrows that are pointing around. These are, again, these little attractions that you see that this particle can experience. There's particle attractions all around it right now. And as you might kind of surmise here, attractions around are a good thing, right? These are attractions that are happening because attractions in general make things a little bit more stable. Whereas at the top here, you don't really have attractions towards the top of the surface because this is the surface. There's nothing here for it to be attracted to. Whereas it does have attractions down here towards the sort of sides and the bottom. And so, right, if you think about it, just in general, particles as a whole, would they rather be here in the middle, or would they rather be towards the surface? Again, as if they had feelings and had desires and wants. Energetically, though, is it better for the particle to be towards the middle or towards the surface? Towards the middle, most definitely. So they actually minimize the surface. And there's kind of like this overall inward pull and overall inward tension. And as a result, that allows you to like have this surface tension on top. Capillary action, this was one where you basically have fluids that can flow against a pull of gravity, so attraction of the surface of a liquid to the surface of a solid. And the liquid travels up, again, lots of times narrow tubes or narrow surfaces because there's that strong attraction of the liquid. So you see right here, you have, again, kind of like a generic large volume of liquid. Here are some smaller and smaller tubes that are getting closer and closer to a capillary size, I suppose. And you can see that, there's not like there's extra attractions or extra force being applied, right? It's just that you do see that the liquid level gets higher and higher compared to the original size of your sample right there, or the original height of the sample that's inside this tube. And again, as you go towards the top of this, towards the right anyway, the surface tension, the capillary action, again, seems to be in greater degrees as the tube, as the opening gets smaller and smaller. Because these water particles are going to be able to attract or be attracted to the surfaces of the glass of the tube, and that draws the liquid up. You can see that paper, for example, plant roots, blood vessels, they all utilize capillary action that allows for there to be a flow, even though gravity might suggest otherwise. Another property about water, or liquids anyway, is something called viscosity. So essentially it's the resistance to flow. So the higher the intermolecular forces of a substance, the higher the stickiness, right, of the particles. That means it's more viscous, meaning it's less likely to flow. It is more resistant to flow. So a classic example right here would be water, for example. Water, you can pour that out no problem. It's going to flow out fairly readily. But then in comparison, oil, right, like cooking oil, vegetable oil, that when you pour that out, you can tell there's a little bit of a delay that from when you tilt the glass and when the flow of the oil actually comes out. And so this difference, again, shows you that it's pretty obvious that viscosity is something that you can see. And you can actually measure, and there's ways to do that. And we won't really get into that, but you can also compare them very readily. So oil is considered to be more viscous than water. You can see here on the left, this is going to be kind of a little chart just showing generic comparisons of the viscosities of various substances that you might be used to. And the top right here, this is actually a little picture of a scientist who worked something with this substance anyway. It's called pitch, and there's actually a little story behind it. We'll get to that later on. But that's what viscosity is about. Evaporation versus boiling, this is kind of information that I think you'll recognize, but the idea here is that vaporization, this is the broad umbrella term for when substances that are in liquid forms or even gas become a vapor. That's vaporization. But within vaporization, you have two subcategories. You have evaporation and boiling, right? So evaporation, this has got the little extra E in front of it. That basically says that this is where you have vaporization occur at the surface of a liquid. And boiling then is actually vaporization, where it actually has vaporization occurring all throughout your sample, not just at the surface. All right, last state of matter here, solids. Kinetic molecular theory basically says that the particles are densely packed. The particles typically adopt an orderly arrangement, which we are kind of familiar with, right? We know that the solids typically arrange themselves in a very obvious repeated pattern. Intermolecular forces here have a much greater effect than the other ones because the kinetic energy is fairly low. So the intermolecular forces can hold them in place. And then finally, part 4 here, the particles are fixed. Generally speaking, they don't flow past one another, right? The movement is limited to vibrations, not flow. So last little bullet point here, solids and liquids, they're collectively called condensed states due to the small amount of space between the particles. That kind of makes sense, right? They're condensed, forced into smaller spaces. Some solid properties here, you should know that they have definite shape and volume, which makes sense because, these particles aren't going to just move about and to fill up whatever container it's in. So it's the definite shape and volume. Definite melting point. There's a little unfamiliar maybe because we haven't talked much about boiling and melting points, but there's a very defined specific temperature at which substances, solids will melt. And that's not true for boiling point, and that's something we'll get to later on. High density, as we mentioned again a minute ago, that's got to be a compressed state, so it's higher density. And of course, it's incompressible, right? We can't really take a solid and make it forced into a smaller space because there's not a lot of space for it to be forced into. Finally, this term diffusion, we typically think of liquids and gases as the only substances that can diffuse. And, at least for what we're used to saying, yeah, that's absolutely the case. But it turns out that solids can diffuse into each other. So in this example here, we have a sample of copper, right? We have a sample of nickel, and these two are going to be put next to each other and effectively clamped together for a long time. And, over a long time, it's something that we can observe, and it's a little bizarre, a little surprising. But it turns out a couple of atoms will actually sort of replace each other, right? They'll kind of swap places with each other. And this diffusion, again, is basically saying that these two particles will eventually start to diffuse into each other because they do have some motion, right? That motion is generally limited to vibrations, but sometimes that vibration can be big enough to where it swaps place with another one. All right, to wrap up solids here, we're going to take a look at the two types, and this is also potentially review, but just to reiterate this idea that solids generally have two categories in terms of their structure. One would be crystalline, and the other is amorphous. Where crystalline, you see that it has a crystal-like structure, meaning it's a three-dimensional repeating pattern, or at least a geometrically repeating pattern. So right here on the left, right, kind of separate these two. This is an example of crystalline solids, where in the particle level, you can see that these are arranged in that very nice, solid, rigid repeating pattern. Just a quick comment though, again, these little lines right here, these are not really actually present. They're just showing you the connectivity and sort of that geometric pattern. It's a lot easier to see that pattern anyway with those lines present. But the idea here is that, yeah, if you look at it more on a macroscopic scale, right, so this is just looking at it really closely, and you can see that there's a bit of a sort of repeated pattern here. It kind of looks a little bit like a square, like a cube almost. And that sort of reflects the fact that these particles in the particle level are also kind of in a cube shape as well. And so that's why it's nice to see that you can see the particle level also reflect what happens on the more visible level. In comparison, you have amorphous solids here. So amorphous, A meaning not, and then morphous referring to shape. So really not a defined shape here. The particles are a little bit more random in their arrangement, and you can see down here on the bottom, this is an example of what the particle arrangement might be like for an amorphous solid. And that's kind of what you see here at the top. So this is an example of an obsidian arrowhead. Obsidian is a mineral, and it's very distinctive in that it doesn't really have a nice clean shape, kind of like you would see over here with the sodium chloride example. And that also makes for some nice jagged shapes that you can see, because this is used as a nice arrowhead, and those jagged shapes allow for some extra sharpness, which makes the arrowhead a little bit more effective. But again, that's reflecting the fact that down here on the particle level, these particles are arranged in a non-obvious repeating pattern. Alrighty, that'll do it.